This is from section 12.1 through 12.4. 12.1, we started talking about Hooke's law and the basics of simple harmonic motion. So let's quickly talk about Hooke's law. Hooke's law tells me that the spring force is equal to negative kx. What's x? What's x, Marianne? Okay, and specifically though for springs, don't just use displacement. What would you say x is really? Not distance across. Give me more for springs. X is displacement, yes, but for springs.
Like stretched minus, or compressed minus regular, or whatever, what is like the distance from...
Compressed minus regular, that's one way to say it. What's another way to say it? Just, or, instead of stretched, the other word, compressed. How much it's been stretched or compressed. Again, X is how far it has been stretched or compressed. If it's stretched to the left, label X as negative. If it's stretched to the right, label X as positive. If it's compressed, but you compress it left, label X as negative. If it's compressed, but you compress it right, label X as positive. Okay, now, when you compress or stretch a spring, what happens to the spring? What does the spring want to do?
It wants to pull back in the
Wants to pull back. Very good. The opposite direction is the key there. So this is always opposite the direction of X. It's the key there we have to remember. If it's pulled to the right, the spring pulls back left. So if the X is to the right or positive, then Fs is negative. Okay, the stretch in the spring is always opposite the direction of the displacement of the spring or the stretch of the spring itself. What is K? Okay.
So is the problem going to be like it goes from like 5 to 15, or will it just be like it's stretched 20 meters, or it could be anything?
Yes, exactly. Either of the two.
So if there's a problem and instead of it's the spring force, it's the applied force, would you just label the applied force negative and then solve the problem?
So that's a good example because I think it was in your lab, you have to consider the negative or positive part. The applied force is always the opposite sign of the spring force. Okay? Because if you pull on a spring this way, or you pull this way, the spring pulls back that way. The applied and the spring force themselves are opposites. Remind me to come back to that for a second. What is K? What is K? Spring constant. Tell me in an example what K is. How would you describe it with an example? The more this, the less this, or how would you say?
Like rigidity.
Rigidity?
So,
Okay.
is that how you say it?
Rigidity.
So it's like if in a terminal, like residential, there was a train and it was going too fast and it needed to stop. It would be really large coils to absorb the shock of the train.
Yeah, so it'd be really strong coils. Or large, you don't know. Because the metal lamp, but big diameter could be small. So yeah, the idea of K is really the strength. So, for example, I've got two springs, right? One's hanging, they're different. And for both of them, I pull them so that they both stretch the same distance. Okay? Two different springs, I pull on them, they stretch the same distance. If they're different springs, what can I conclude about the forces I'm applying? If the K values are different, but I pull on them and I stretch them both a certain distance, the same distance as each other, what can I conclude about the forces I'm applying?
Then wouldn't one force be greater than the other?
Good. Why?
Because one of them has a higher K value.
Exactly. So a higher K value means you need to apply more force to stretch it. That's really what we get from Hooke's law here. So graphically, that would look like this, right? Let's look at like what a graph would look like. If I look at the applied force, instead of the spring force, I'm looking at applied. And I look at X. What do I know? As I apply more force, the spring stretches more. Okay? If I apply negative force, it compresses more. So here, if it compresses less or compresses more than the negative. That's my definite correlation here. As I apply force, it stretches or compresses in some distance. Now, remember, the applied force is always in the same direction as the stretch or compression. Think about it. You have a spring. Here's the spring right here. Here, this end is fixed. Okay, this is fixed. I push against the spring. Which way is my push? Which is? Which way would the compression be also? So the applied force and the compression are the same. Same thing with expansion. I pull on it. I'm pulling this way, positive. Which way would it stretch? Also positive. So applied force is always in the same direction as x. So as one goes up, the other goes up. So we see that direct relationship there on that graph. For a spring force, instead of it being a positive, it's a negative. So look at this. This graph here, this graph here is similar to this equation, except I'm using really this equation. If this were the applied force instead of the spring force. So when it's the spring force that we're analyzing, it's a negative because the spring pulls back. But when it's the applied force that we're analyzing, we can leave it as a positive, really. And you can leave it as F equals kx without the negative because you're looking at the applied force there. So if I were to look at this mathematically, isn't this really just y equals mx plus b? That's really all it is. And take a look. If I write that down, ready? Y is really f. Well, take a look. F is on the y-axis. X is still x. So what is the slope of this graph defined by? K. It's the k value. The k value is the slope of this graph. Okay, the k value is the slope of this graph. And we saw this on the first day, but we looked at a data table. The data table showed us that the slope was constant that first day in section 12.1 for this entire chapter. Okay, so the slope is k. What is the y-intercept of the graph? 0. So that's why there's nothing at the end of here. So b is really 0. We don't really need b. Alright, so again, the slope of this graph is the k value. Slope of this graph is the k value. How do I know that? Take a look. What's the definition of slope? Slope is change in y. I'll put it down here in the bottom right. Slope is change in y over change in x. Well, y is force, x is displacement. So if you have more force, you have more displacement. So if you increase this, this will go up. If you increase it further, this will go up. But every time you increase force, you also increase your stretch of your spring. So every time you increase this, it goes up by the same increase. Therefore, this gives you a constant, and that constant, again, is defined as k. Jake, then Victoria.
So basically, whenever x is positive, the fs is negative, and then you should only ever have a positive k value, right?
Absolutely right, both statements.
Okay.
Yep.
So if it was being compressed, then it would, like, the line would be going from up there.
Believe it or not, it would still be the same, actually. Because even if it's, well,
Like I was like,
sure. In the bottom left quadrant, it would be
Oh,
over.
okay.
Yeah, but the general trend is you apply more force, it stretches more.
Okay.
Think about it that way, because yeah, what Victoria's saying, what if it was compressed, right? Then the applied force is negative. So then the applied force would be below the axis, well then it would stretch negatively, so it would look like this. You'd have a negative force, meaning it's down here, and a negative stretch, or a compression, meaning it's down here. But it would continue this line. Okay, so this is what I was trying to draw in the other class, and now it makes sense. I was trying to visualize this, and I was having struggles visualizing it. But that's what this would look like, actually. It would continue. That's really good that you asked that, Victoria. So a negative force means a negative displacement, which is compression. So here, this is like compression here. And this is stretching, or expansion. I'll just put stretching. Okay? Assuming, obviously, right is positive and left is negative. All right. What else about 12.1 did we talk about? We talked about the nature of a mass spring system and a pendulum system and how they are analogous to one another. What did I mean when I said that? You better recall. How are mass spring systems similar to pendulum systems? right, way to put it. They have the exact same pattern. So ready? I'm going to demonstrate it for you up here. So imagine you have a mass attached to a spring. Here's the spring or the wall. Here's the mass. So the spring is between my hands right now. If I stretch this spring and let go, the spring does this, right? It oscillates back and forth, back and forth, back and forth, and eventually it stops. Well, if you look at a pendulum, instead of pulling on the spring and letting go and doing this, you raise the pendulum up and let go, and the pendulum does this, doesn't it? And eventually the pendulum teeters off into equilibrium. It's identical to motion. So as the spring moves, the pendulum rises. As the spring stretches, the spring then comes back, passes equilibrium. That's like the pendulum passing the bottom, equilibrium. Then the spring gets compressed. That's like the pendulum going up to this negative angle. Then it goes back. Then it goes forth. So this is rotational, right? Harmonic motion. This is linear harmonic motion. But the ideas are identical to one another. When the spring or the pendulum is at equilibrium, right? Ready? So here we go. We stretch them both. We start them both here. We let go of both. The spring pulls back. The pendulum pulls down. Well, when they're at equilibrium here, when they're at equilibrium, what's the net force when you're at equilibrium? Zero. So when they're in the middle, at equilibrium, there's no force and there's no acceleration. Because if there's no force, there's never acceleration. But they do have something at the middle. What do they have? Velocity. And at the middle, the velocity is a max. Think about it. Starting from rest up here, just look at the pendulum. Starts from rest, you let go. It picks up velocity until it's the bottom, then it slows down. Then it speeds up. Then it slows down. Then it speeds up. So at the very bottom is when you have the max velocity. It's the same as the spring. When the spring is oscillating or the mass is oscillating, when it passes equilibrium, it's got max velocity. You stretch the spring, it's not moving, you let go. It picks up speed, it picks up speed, it picks up speed, it hits equilibrium, then it starts to slow down. Because now the spring is being compressed. And then it stops. Then the compression pushes it out. It speeds up. It gets to max speed. It slows down. It stops, etc., etc. Jake?
There was a question on the problem set that asked, like, can the pendulum move? It was the one about no constant acceleration. Do you remember that one?
I don't, to be honest.
Yeah.
Do you have it in front of you? Can you pull it
I
up?
like that expert,
Yeah, take a minute, pull it up. I'm gonna make another comment, Jake, while you're looking.
Mr. Hall?
Yeah.
It's like about, it was also about a pendulum, but
Yeah.
there was one of the problems, and it was saying how, if it was like the time was off on a pendulum, what would you do? And was it like, it was something like that, but I don't know if that, it doesn't really refer to this probably.
Do you remember that one,
What was
Kev?
the question? It was like, the grandfather clock's running too slow, so what would you do to like fix the time?
Would you like
Shorten
make
the
the string
length,
longer?
shorten.
Oh, you shorten the length.
Shorten the length of the bottom. On the string, not the bottom.
Alright, the question is, does the acceleration of a simple harmonic oscillator remain constant during its motion? Is the acceleration ever zero?
So, what did you just write down? When it's at equilibrium,
It's at zero.
okay. Now, when it's pulled completely, right? So imagine your spring, it's at equilibrium, it's relaxing, it's nice and calm. You pull on the spring. When you pull on the spring, you're creating a force in the spring, aren't you?
Yeah.
So that means that there's acceleration there.
Yeah.
So as soon as you let go, it's got acceleration. That's what causes it to move, that acceleration. Until it hits the middle, and then it's got no acceleration, but at this point it's got velocity. So now it's going to keep moving because of its velocity, not because of its acceleration. Then it starts to slow down with a negative acceleration, meaning it's slowing down until it stops. And at this point now it's got acceleration this way, causing it to move back.
Is the
It's the
reason
middle.
it stops because of friction?
No, it's because of the spring. The spring is what's causing it to oscillate back and forth. Okay, but there's acceleration at the ends, and there's velocity at the middle, and vice versa. There's no velocity at the middle, and there's no acceleration in the middle, and no velocity at the ends. They're opposite of one another. Look at the table on the second page of your notes from section 12.1, if you want to review what I'm saying here. Okay, second page of the notes for 12.1, I think it is. All right, what do we call... question?
If there was no friction and you did like the mass on the string of the pendulum, and they were going at the same time, would they both like correspond to each other?
Yeah, identically. It's actually kind of cool. So if you were to make a system so that they had the exact same period, so that you made radical L over G equal to radical M over K. Remember the period is 2 pi root M over K, 2 pi root L over G. If the quantity L over G were equal to M over K, then you'd have the same radicand. 2 pi is the same, which would give you the same period, and they would literally move in tandem. Yep. Assuming no friction, obviously. Yep. And there's probably an animation. If you remind me in the second period, when you guys are doing your lab, I'll pull up an animation of that so you can literally see them moving in tandem. Okay? Just remind me, please. What I was going to say was, what is the term called that we've been using for maximum displacement in either direction? What did we call that? We really talked about it more in like section 12, 3, and 4. What was it called? If you were to graph the motion of a spring, right, of a mass spring system, here's what it would look like. Ready? And when it gets to the top up here is when it's stretched completely. Then you let go, comes back to equilibrium, and it goes negative, and it goes back to equilibrium, and it goes positive, and it goes back to equilibrium. So when it's at the ends, when it's at its maximum displacement, what is that called on the graph? Amplitude. Very good. Good vocabulary. So the amplitude, we know, is the height on the graph, right? We talked about that for graphs already. The amplitude is that height on the graph, the max height. Well, the amplitude is also the max displacement in simple harmonic motion. So, for example, let's look at a spring and a pendulum. If this spring is oscillating back and forth, here's equilibrium. And let's say it's oscillating back and forth like this. Okay, you pull on it to stretch it out to here, and it just oscillates back and forth. Well, that displacement, this from here, let me put some red lines from here to here, we call that the displacement, right, or the stretch of the spring. This is also known as the amplitude. What about for a pendulum? For a pendulum, what's the amplitude? What's the amplitude for a pendulum? Right, so again, the amplitude here is the delta x, the change.
Is it at the top of the thing?
But give me a variable, like parameter. What parameter represents amplitude for this?
Like a degree or something?
Yeah, there it is, like a degree. What's that? So an angle, very good. Like a degree. Okay, so that's the amplitude when it comes to a pendulum. So for a pendulum, you raise it up to a certain angle. That's also known as the amplitude. And it's going to oscillate back and forth. So it's got positive amplitude, negative amplitude, positive amplitude, negative amplitude. And what you would see would be the sinusoidal motion, this little wave again. Definitely remind me for an animation next period, please, okay? I'll pull one up so we can look at it. Cat.
Would 45 be the maximum?
No ideal or anything like that. No. You could go all the way up to like 180. You could technically take it, put it all the way up here, and let go. If it wasn't a string, if it was like a rod, the rod would just go whoop and whip down. If it was a string, it would just fall. But I mean, you could raise it as far as you want. There's no limit to it now. Okay? You get the idea of amplitude? It's good to know our definitions for sure. What's period? Now that we're on the terms or the ideas of definitions.
Well, it's the time it takes for like a pendulum to go back and forth. It takes one. It's the time it takes for one cycle, basically.
And for a pendulum specifically, it doesn't just go one way, it has
It
to.
goes the other way.
Good. So for a pendulum, the time it takes to oscillate back to its original spot. For a mass spring system, you pull on the spring, you let go, the time it takes to come back, compress, and come all the way back to where it started. Right? The period, again, is the time it takes. The time it takes. What is the frequency? What is the frequency?
It's like amount of movements per period.
Yeah, the amount of cycles per period. The amount of oscillations every period. Okay, it's inversely, write this down, inversely related to the period. inversely related to the actual period. The frequency. Okay, so again, frequency. So period was tau. Let me just jot these variables down. This was tau. That was the period. And this was the time it takes for oscillations. Then omega is the frequency. And this is the amount of cycles or oscillations per period length. These are inversely related due to the equation that states, it doesn't matter how we state it actually, but I think in your notes I put it the other way. Omega equals 1 over tau. So the frequency is the reciprocal of the period.
Tau equals 1 over omega too, right?
Yep. Flip-flop them, yeah. So if I told you that the period length was 4 seconds, here's what it physically means. Watch my arm, please. It means this. 1, 2, 3, 4. Okay? That's all it means. Now, next, how many cycles are completed in 1 second? Again, ready? Just follow me. 1, 2, 3, 4. After 1 second, how far did I get?
Half a cycle.
Not half.
1/4.
1/4. Remember, this is half. This is a full, so this is only a quarter, right?
Right.
So think, again, logically, it takes 4 seconds, Jake, it takes 4 seconds for a period, so it's 1/4, reciprocal, 1/4 for the frequency. It literally does 1/4 of a cycle every second. Another fourth, another fourth, another fourth. Completing 1 cycle in 4 seconds, as an example for you. Okay, but again, the idea of that is that if the frequency is a very high frequency, it means this, ready? Back and forth real fast, or a spring oscillating back and forth real quick. That's high frequency. Okay, high frequency, you been to the dentist before? Ever get a cavity filled?
Yep.
Or ever get your teeth cleaned with the water pick thing, where they like
Yes.
spray high velocity water? Ever hear the sound of it? It's like, you hear the like change in pitch that goes up as they like, go into your teeth. It's because the speed is changing as it digs into your teeth. So that little drill they use, it's actually a drill. A drill with super high frequency gets pushed into your tooth, and you can hear the change in frequency because it's grinding away your tooth. So it's lowering the frequency as it touches your tooth. So it has to do with how fast something vibrates or oscillates or spins. Frequency is also spinning. So a car spinning is like a frequency also. The frequency of the tire. If it spins faster, it's got a higher frequency. If a mass oscillates quicker, it's got a higher frequency. Okay, so frequency is a measurement of how many cycles occur, how quickly those cycles occur. You okay? You look upset about something.
Keep singing and pushing the table.
You alright?
Yeah.
The wheels are, I think the wheels are broken, so just,
I'm just proving my hands are above the table.
oh, just don't put your feet on the legs for sure. Alright.
It's you.
What else? You should be able to understand how to solve problems where you have like a general change. For example, let's go to a new slide, right? So right? So if you were to increase the length of the pendulum by a factor of 9, you increase the length of the pendulum by a factor of 9. What happens to the period of oscillations if you increase the length by a factor of 9?
It decreases, right?
Numerator this time. Numerator.
Oh,
But by what factor though? Because it's under a square root.
3.
3. Very good, Kat. Awesome. So how do you do this? You take a look at it and you visualize and you say, okay, well, if I'm increasing by a factor of 9, it's like putting a 9L up top, right? And then the radical 9 comes out in front as a 3. Okay, this really simplifies to become this. Again, this 9 is a square root 9, which comes out front as a positive 3. So if you increase the length of a pendulum by some number, the period goes up by the square root of that number. So if I increase the length of the pendulum by a factor of 25, this becomes 5. 5 times the period. Okay? This was something you made a conclusion with in your lab. So again, labs, really good to study from labs always. All right, let's talk about interference for a little while. We have destructive and constructive. What's the difference? Interference.
In constructive interference, they're going the same way, or like they're on the same, I guess, like side of equilibrium. It's like if they're both positive, when they meet each other, the resulting wave is higher.
Good. And then what happens after that?
Then they just go back to normal.
Good. We understand constructive. 2 positive pulses. When they meet or when they coincide, they kind of join, and then they separate and go back to where they were going.
Doesn't one of them have a fixed,
I think you're thinking of a standing wave.
wait,
Fixed
fixed
point.
boundary, free boundary? Does that have to do with constructive and destructive?
That has to do with the way the wave is reflected when a wave pulse is sent to something.
But aren't
Boundary.
isn't destructive interference reflected?
Destructive and constructive is only when 2 separate waves collide. Not when you send a wave and it gets repelled. So imagine this. Ready? Watch.
Because
Jake.
in the image it said that one of them looks like it's being reflected.
Yes, because it looks like it's on the bottom, right? So you go destructive. All that is you're sending a pulse. That pulse is sent back. But if 2 pulses, Jake, I'm answering your question. Folks, if 2 pulses come together like this, that's destructive. When you send a pulse through a rope, and the rope is fixed, and it sends the reflected pulse back, that's not interference, it's just reflecting a pulse, that's all it is. You need 2 waves coming together. That's one wave that's moving back afterward, okay?
Is this the same way as like finding the sum? Like the sum of their waves?
What is that called? What's the principle? Anybody remember? Start with S.
Superposition.
Superposition principle. Good word to know for sure. Superposition means that if 2 waves have positive amplitude, you just add them. Or anytime you got amplitude, you just add them. Is it literally unable to lock?
I don't know if someone's pushing it or not.
Can you not, like, does this not click down right here? Look, that's locked. Stop it altogether, right? Thank you. Because you guys are losing focus there, that's why.
I was pushing hook in the gut.
Anyway, what?
Sorry, can you take the definition of the superposition?
Sure. So superposition principle states that the sum of 2 amplitudes of waves coinciding give you a third resultant wave.
I'm still unclear as to the difference between constructive and destructive.
Okay, so imagine if you have a first function that looks like this. Okay? And then you have a second function that looks like this. Now, let's say this is a function of time. All right? And we want to know what would the resultant wave look like using superposition. Well, in the beginning, look at the first instant in time, right here. Both of these waves are positive.
Yeah.
So I would add them together. That would be constructive interference. So the resultant wave would start out up here somewhere, above. Right? Until this wave becomes pretty much 0, right? At this point in time, this wave has no value at all. So if I add no value to whatever value this is, it stays at whatever value this is. So the resultant wave starts to decrease at first. Now, as soon as one of the waves becomes negative amplitude and the other is positive, what kind of interference is it?
Destructive.
Destructive. So now, this wave continues to decrease because the other one's decreasing, until, we really need numbers, by the way, to do this properly. Say this were negative 10, and let's say this up here was 10. At this instant in time right here, we call this point-to-point sums. Have you done this in math, point-to-point sums ever? You think about like a vertical line, and you just add at that location. So what would the blue line's value be at that instant in time? And what would the red one be approximately, maybe?
Maybe 7.
7 or 8, somewhere in there, right? Something like that. So since this value is around 7, and this is around -10, -10 plus 7 gives me -3. So that means the resultant wave needs to be here. So that tells me that I can kind of connect these lines. And if I do this enough, I could eventually get the resultant wave. If I do it again here, I'll see that they're both positive. So I'm going to be adding them together, so it's going to end up somewhere up here. So this wave is going to eventually come back up like that. So take a look. The resultant wave, if I keep doing this, can be generated. If I put an infinite amount of vertical lines and come up with the resultant wave every single time, I can see that. Another animation I need to show you. Second period. Those two things. So an animation of the oscillations at the same time, and then also superposition. I can show you something for this too. It might help.
So constructive interference doesn't have it reflective waves at all.
That's a totally different topic, yeah. It's also,
when we talk about it, we shouldn't even include it.
one is interference, one is reflection of waves. Different things.
Alright.
So it's not like two different scenarios, like if you were given a graph and you'd say that's destructive or constructive, it's just like at a certain point it's one or the other?
Yes, but you can have some graphs that are all constructive and all destructive. It depends on the graph. It really does. So like, what would a graph look like that was all destructive interference? What would it have to look like? It's a very simple answer. For all destructive interference.
It was always in negatives? Or
One negative, one positive.
One negative, one positive. What's an example of constructive interference?
Two positive.
Or?
Two negatives.
Good. So it depends on the graph, really. Or you could have a graph like this, where it's just kind of crazy, and you have to figure out which one is the resultant wave if I give you 3. Or tell me, at 3 seconds, is it constructive or destructive interference, and where is the resultant wave at that point in time? Okay, so maybe like this is 3 seconds right here. Here's the resultant wave, and it's clearly destructive interference.
So it's saying like one, so like if you ask us the difference between them, it's saying one of them has a negative and positive wave and one of them has 2 positive and 2 negative is sufficient answer.
Yeah, but I might like word it a little bit better. I might say that with constructive interference, the resultant is a greater value than the original in magnitude. Whereas with destructive, they cancel each other out, so it's always less than the original. Okay?
Does this for the constructive or for
Destructive.
Do they have to be from the same source? Like if you send out a pulse and it goes and like tension brings it back on that way, you send out another pulse from the same direction you originally sent it out, could they both be constructive? Or would they be deconstructive?
It depends on the way the pulse is returned. So ready? I send a pulse to a loop on a rope. Well, that's going to send a positive pulse back. As the positive pulse is coming back, if I send another positive pulse, it's constructive. But if I did that with a fixed end, it would send a negative pulse back. And if I send another positive, it would be destructive. So it depends on the scenario. Yeah. All right. Let's talk about nodes and antinodes for standing waves. Is the concept of what a node is and what a standing node is, a standing wave is, and what an antinode is. Okay, being able to describe that. So what's an example of a standing wave? The simplest one you could think of. It was one I gave you in class. It was really easy to give an example of.
It wasn't like sound, or was it something else?
It wasn't sound.
Was it like guitars and when you draw it to separate it?
Yeah, a guitar string. So whether it's a guitar string fixed at 2 ends, right? The guitar string looks like that, and it will look like this, and it will go up and down like that as you pluck it. Or maybe it's a guitar string or something else that's fixed in the middle also. Okay? And maybe as this part's high, this part's low. And as this part's low, this part's high over here. And these oscillate up and down like that. Or maybe there's 3 of these. All right? What are the nodes? What do nodes mean?
They're like where they, like little circles where they stop, or like it's like a break in it or something.
A break in it where they stop. What's another way we can say or describe a node?
Is it a fixed point?
It's like a fixed point where there's no oscillations at all. Okay, so the nodes are here, 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 okay? Wherever you see the ends, I'm just writing on there. Those are all the nodes, where all those dots are. An antinode is?
Basically like a high point of a wave.
Good. High or low point. So there's one antinode here, one antinode here, one antinode here. Again, there's not an antinode on the top and the bottom. It's just one antinode because it's the same string. Look at the guitar string example. This piece of the guitar string is here right now, but once it starts to move, it ends up down here. It's the same antinode. It's one antinode right here down the middle. So remember that antinodes are always equal to the nodes, but minus 1 from the nodes. I wrote that the other way the other day, as nodes equals 1 plus antinode. Same thing.
To get one antinode, do you need a high and low point, or just one or the other?
You will have to have a high and low point because the only time you have nodes and antinodes are for standing waves, and with standing waves you always have high and low points. Okay? What else can I think about? What's the difference between longitudinal and transverse waves?
Longitudinal are parallel to the motion of the wave, and transverse are perpendicular.
What do you mean R? You said R. What R? So
The
longitudinal R.
longitudinal waves are parallel to the motion of the wave.
Everything's right except for one thing there. Pat?
Particles vibrating.
Particles vibrating are parallel to the wave motion for longitudinal. Particles vibrating are perpendicular for transverse. And remember, transverse, think about a rope. Think about a rope. The rope is going to be vibrating up and down, but the wave you see moves left to right. Think about the slinky doing this with longitudinal. The wave you see pushes left to right, and the vibrations are left to right. So those are parallel in that instance or that circumstance.
To the wave, you said?
To the wave motion. Definitely study your lab. I'm just going to leave you with that for that part. Because there's definitely questions from your lab, like directly from your lab. Like, as seen in your lab, blah, blah, blah. If you submitted your lab hard copy and you want a copy of your answers, just come by and make a photocopy real quick. You can just take a copy. It doesn't matter. Or a picture. Or just redo the lab. It's a blank. I wouldn't redo it, actually, because it involved apparatus. Let's see. We talked about periodic and pulse waves. Periodic and pulse. What's the difference? Or how are they related to one another, rather?
A pulse wave is one wave sent out at once, and a series of waves is, a periodic wave is a series of waves.
Good. So a periodic wave is just made up of a bunch of pulse waves that are generated. Usually, when you have a periodic generator, it generates them at some constant interval. So like every second you see a flick or a rotation every second. Okay, that's when you see periodic waves.
The pulse wave is a single wave.
And what?
Pulse wave is a single wave.
Is a single wave that's being sent somewhere, yes. I want to do some math stuff also. Go ahead, question first.
Do you know an example of all the different kinds of like waves and all that stuff? You know what I mean? Like,
No, I don't.
A specific example of like a periodic wave, like a pulse wave.
All right, well, a pulse wave would be, imagine, I'm trying to think of an easy example, a ripple in the water. Like you take a rock and you like just throw one pebble, just one though, into a pond. It's going to propagate that. That's one pulse. It's just moving outward. Okay? Versus, a little kid sitting there with his feet in the water, kicking the water over and over again. That'd be a periodic wave. He or she is constantly generating pulses after the other. So you keep seeing these pulses go out. Whereas the first one, a pulse lands and it just goes out, and that's it. Okay? Yeah.
Can we go over waves and energy?
Go over
Waves and energy.
waves and energy. Sure. All right, let's look at waves. Recall that, what did I write? I forget. Is it amplitude equals the square root of the square of the energy?
We never did this.
Oh, we didn't go to do in class.
There's a problem, the problems.
Oh, that was the last thing that you were, yeah. In the notes, right? That I said to read the notes or look at the video for that? Okay. Let me think of a way to word this. All right, so the energy in a wave is proportional to the square of its amplitude. The symbol in the middle means proportional to. The energy in a wave is proportional to the square of its amplitude. And think about this for a second. This is good that we're going over it. Thank you very much. So, if we have a spring, right, and we have a mass hanging from that spring, I'm not going to do that. You can visualize in your mind for a second. So, I'm holding a spring, the mass is hanging from it, we pull down on the mass and let go. What happens? It goes up, and then? And eventually?
Goes back to.
Why does it stop? Eventually.
Because you're not applying force to it.
Good. And what force is slowing it down? Friction. Those two things. You're not applying more force, and friction is slowing it down. Now, friction is really energy, isn't it? So as friction encounters the mass spring system loses energy. Look at the formula, look at the relationship on the board. If you lose energy, you lose amplitude. Sorry, Paul. I know, I saw you winking on it. Sorry. As you lose energy, you lose amplitude. So think about the mass spring system. You pull down and let go. What is it doing over time? Isn't it losing amplitude? It's got the max amplitude to start. It lets go, and the amplitude only goes up so far. And then it goes down so far until it eventually stops. So the idea here is that the more the amplitude is, the more energy you have. The more amplitude, the more energy. So for example, if the amplitude doubled, if you double the amplitude, what are you doing to the energy really? If you double the amplitude, 4, not double. Again, look. Stay. First of all, we have examine, and then we have double. You double the amplitude, you're doubling it, but you're squaring a double. So it would increase the energy by a factor of 4. Alright? The idea behind that they're related to the square of that. The square of it. Let's pause and do an examine. We've got this, and the last one was V equals omega lambda. By the way, what's lambda again? Because I haven't even gotten into that yet, but we did it yesterday. Wavelength. Good. Wavelength. And we can see that, although it's obvious, look up here, it's obvious that the frequency and the period are inversely related, right? You can see that. But the wavelength and the period and the frequency are also inversely related. Because traditionally, the velocity of something, assuming the velocity isn't changing, obviously, like an EM wave is always 3 times 10 to the 8, speed of light. If this is always the same number, if I decrease the frequency, I need to increase the wavelength to get this to be the same number. If I were to decrease the wavelength, I have to increase the frequency. And again, go back to what your animations or your graphs look like here. If I have a graph like this versus a graph like this. This one, look at the wavelength. The wavelength is from here to here. Crest to crest, trough to trough, or just starting point to starting point. So this is the wavelength, one full cycle. Whereas here, this is a wavelength. Doesn't matter where I pick, remember? So which has a bigger wavelength? Clearly. So as a result, the first one has a bigger. Again, the wavelength is bigger on the second one. So what's bigger on the first one? What parameter are we each talking about? The frequency. The frequency is how many cycles occur. Which one has more cycles occurring? Clearly the first one. So the first one has a lower wavelength, therefore it's got a higher frequency. Okay, so we've talked about how period is inversely related to the frequency, but the wavelength is also inversely related to the frequency. Let's go back to math now. You can definitely expect to have a problem which involves either solving for k or figuring out k at some point and then using it again. Let's look where that might be. Look here. Look at these two equations. What are these both involving?
K.
Yeah, so therefore they both have what physically? What? A spring. So for a spring problem on the test, you could expect something where maybe you're given the period and the mass that's attached to the spring, and as a result, you use this fourth equation to find K. And then I tell you, all right, if this object were under a force of, 17 newtons, and you know K, you can use the force and K to figure out how much it's being displaced by. Or vice versa. Maybe you need to figure out K first from the Hooke's law equation. I tell you, you apply a force of 10 newtons, it stretches 1 meter, 2 meters, so therefore it's 5 newtons per meter. Well, that's K from the first equation. And then I say, well, now you release this object and it moves in a harmonic motion. If you know K, and I tell you, obviously you need to know the mass, you can find out the period. Or maybe you know K from the first one that you get, you know the period, and you can figure out the mass of the object being applied. Alright? Now, there's a difference, though, between mass and force. And this is something I need to point out. Because in your homework, in your lab, in your problem sets, I'm seeing this mistake over and over again. So if I have the mass of some object being suspended from a spring, I cannot use Hooke's law. I cannot use Hooke's law right now. I need to know what the force is. So how do I change what I know?
What did you multiply by gravity for acceleration?
Yeah, gravity is
9.81.
good. So recall that if you have a mass, it means that gravity is pulling down on that mass. If gravity pulls down, what pulls back up in this circumstance? Gravity's pulling down. What's pulling back up? What force? The spring force. The spring. No normal because you're not on a surface. Remember, only on a surface do you have normal force. So, for an example like this, if you're given the mass, say I give you a mass and I tell you the mass is 2 kilograms, and a mass of 2 kilograms causes a displacement of negative 0.25 meters. You can't use Hooke's law right away. You need to first do this. Now, this force is acting down, so it's negative. So I'm going to put a negative here. So this 19.62, it's not my answer, I'm boxing it though, is the force acting down on the spring as a result of the mass. If that force is acting down, then what can you conclude is acting up? Yes, very good. So if this is true, you need to conclude this. And now you can use Hooke's law. I'll put it at the top. All right, now you can use Hooke's law. Take X, plug it in. Take Fs, plug it in, and you will get your answer for K. And K will be positive. Because X was negative, the double negative on the right side leaves K as a positive here. So please understand the difference between mass and applied force. If I just tell you a force is applied, that's F applied, so Fs would just be the opposite. So if you're told a force is applied on a spring and the force is 10 newtons, well then the spring force is negative 10 newtons. You're given that. But if you're given a mass that's hanging, then you need to think, well, what is the force? If a mass is hanging, the force is weight. If weight is acting down, the spring is pulling back up. Okay, back up.
If you divide by negative x, fs by negative s, wouldn't it become positive 0.25? Because that is a negative.
Well, you have double negative. A negative negative is a positive.
Yes, then one. Oh, yeah.
Yeah, but then
But then fs is negative 2, because it's negative 19.62.
that's Fg, pulling down. Fs is pulling.
So fs is positive.
Yeah, so let's just plug them in real quick. So we have Fs acting up positive, which equals negative K times negative 0.25. So we see the double negative now because Fs is pulling up. Again, Fs is a reaction. So here's what you can write down. Put a little note. When this is negative, this is positive. If this is positive, this is negative. Okay? Again, those always have opposite signs. Fs and X. me think. Hold on. So remember, weight is a force. If I tell you the mass of an object is this hanging from a spring, you have to convert it to weight. But if I tell you the weight of an object from a spring hanging is this, you have the force already. Keep that in the back of your head, please. All right, how about this one? Follow-up question. Let's say you know the weight of an object. Let's put a little spring here. Bless you. And there's an object there acting down with a weight of negative 40 newtons. Okay, the object, I'm just putting a dot for the object. And as a result of this, the stretch in the spring, the delta x, the actual stretch from this, is 4 meters. Make believe it's like a bungee or a slinky, something that's longer that can stretch 4 meters, whatever. So if this is true, all right, it should be negative 4, sorry, because pulling down. If this is true, find out k right quick. Figure out k. Real quick. I was going to say right now and then real quick. Put them together. So I've got Fs is pulling up. So that's a positive 40. Negative k times negative 4. So what's my answer going to be? 10. All right, so if that's true, here's the follow-up part I wanted to go through. If that's the spring constant, if that's the k value, and then I said the object is released and it oscillates in simple harmonic motion. In simple harmonic motion. As a result, determine the period. Determine the period of oscillations. The period. From what we have here. Jake, what's the formula I would start with?
Tau equals 2 pi times the square root of m over k.
Why didn't you use L over G, Jake?
Because we're not given a length, but we're given a mass.
Good. We're not looking at a pendulum. We're looking at a spring. Now, we're technically not given mass.
Sorry, yeah.
Oh, wait. That's all right. So, that was going to be my follow-up, Jake. So maybe you can help us here.
I mean, that's right.
So now, we want to figure out the period, tau. We know k from part A. 10 goes in for k. That's easy. But what's the mass? You are not given a mass in this problem. What is the mass? How do I figure it out?
Fg equals mg.
Good. So, how would I figure it out?
40
Equals?
n times 1.1.
Good. Very good. So this is really mg. So set the weight equal to mg and just divide by g to get the mass. Okay, again. And again, mass is always positive. So if you have a double negative there, don't confuse yourself. Divide by negative 9.81. Okay, if the weight is negative, then g is negative. It just happens to be the way we wrote it. So the mass would be whatever, what is it? 4.1 kilograms. So that number can then be plugged in for m, and k can be plugged in as a 10, and you solve for tau. Okay, but I want to make sure that we understand this because I remember last year that students made more mistakes with the difference between mass and weight than anything else. Okay? Expect one other question, another question with a pendulum. I'm not going to give any detail about that at all. And then, why is that funny? And then the last one, you can expect something with, remember the equation V equals lambda omega? All right? Expect something with that. So look at your examples and notes. These were plug and chug. They were really easy. This one, you plugged in 2 of them, solved for the third one. I did an example. Was there an example in your problem set where it had like a minimum wavelength and a maximum wavelength? And as a result, you have to find the minimum frequency and the maximum frequency?
There was like a range one.
A range one. Study that. I would study that.
Wait, what do we do for that? Just subtract the 2 amounts that you find?
No, you don't subtract the 2. The 2 answers you get?
2 answers.
Sure, to find out the length of the range. But if it says what is the range, and you get 500 as your min and 1,000 as your max, the range is from 500 to 1,000. That's what you say. you don't have to even subtract them. Okay, it means what are the possible values, like domain and range actually.
Yeah.
I don't get how you do the minimum maximum. You like plug in different things for x.
So if you were given a maximum wavelength and a minimum wavelength, you would first plug in the maximum wavelength, okay? You have a velocity, because say it's the speed of sound, I'll give you a velocity. If you plug in the maximum wavelength, you get the minimum frequency as an answer. Then you plug in the minimum wavelength to give you the maximum frequency as an answer. Okay, so do them as two like separate problems for an example like that. Alright? For your pendulum, be expected to be able to use the formula. We only have one formula for a pendulum. Tau equals 2 pi root L over G. Be able to manipulate that formula. Be able to solve for L, or solve for G, or solve for tau. Any of those, depending on what you're looking for, give a specific scenario. Okay, I really haven't come up with the questions for math. I'm looking at like what I had for my last year's questions, the ideas, but they're going to vary. They're going to change, but the general idea is the same still. Okay, that you can expect spring mass, pendulum, and this last equation, velocity, frequency, and wavelength. All right?